Okay, let's get started. So how was the exam? Terrible. Who said terrible? What do you think? How was it? Hard? A little bit. Pretty hard. Okay. Well, as usual, I'll send the Scantrons in this morning. If we are lucky, we'll probably get the results back this afternoon, but I wouldn't count on that. Most likely, we'll see the results early next week, Monday, Tuesday kind of thing. If you don't see anything on WebAssign by Wednesday, let me know. I'll nag your TA about it. Okay? All right, so today we're going to look at section 3.10. The topic is on linear approximation. And this thing called the differential. Okay, I'm going to start by sketching a graph of a function. Just some random function. Let's have it look something like this. I'm going to go to x is equal to a, which means y is equal to f of a, of course. Okay, so that point is a comma f of a. We know how to find the tangent line. We know how to find the slope, and with a point, we know how to find the equation of the tangent line. Let me sketch the tangent line here, this green line. If you focus on the region very, very close to this point, okay, so let's zoom in on this region right here. What we will be seeing is that we see the curve itself, the blue one, and then the point. And you're going to find out that very close to that point, the tangent line is nearly indistinguishable from the curve itself. Right? No matter how curved this thing is, if you keep zooming in very close to that point, it'll appear to be very close to a straight line. So near the point a comma f of a, the tangent line is not very different from the curve itself. One analogy is that we know the Earth is a curved object. Right? I hope we all know that. But from our perspective, it looks like the Earth is flat. And that's because from our relative size compared to the Earth is very small. So what we can see from where we are is very, very little compared to the size of the Earth. And therefore, from our perspective, our line of sight, the tangent line, is going to very, very good approximation of what the Earth looks like near us. But of course, once we look far away, we can see the curvature of the Earth. So that's the idea of the linear approximation. If we stay very, very close to a point, then the tangent line can be used to approximate what the curve is. I'll write that down. If we don't move too far from x is equal to a, then the equation of the tangent line at x is equal to a can be used to approximate f of x. One of the advantages of doing this is that if the function is a very complicated function to calculate, got log, got exponential, or lots of trig going on, that may be hard to calculate and hard to use. But we know a line is very simple. It's the equation of a line, very easy to use. Nearby that point, instead of using a complicated function, we could use the straight line, right? So that's the main idea behind the linear approximation. Okay, so let's write down the equation of the tangent line. We can use the point-slope form of the equation of a line. Okay. Y minus the y value of the point is equal to the slope, f prime of a, times x minus the x value of the point. Rearrange this a little bit. The equation of the line can be written as f of a plus f prime of a times x minus a. And once again, this is very close to the function f of x near x is equal to a. The term near is a very complicated word, actually. How near depends on what the function looks like, what the behavior of it, how curved it is near x is equal to a. So it's very hard to say. There's not one set number we can say, never move this far away from a. And this is called a linearization or linear approximation of f of x near x is equal to a. And we'll use the symbol capital L to denote that. Okay, instead of memorizing that formula, just remember where it came from. All this is the equation of the tangent line, which you've done many, many times. Write the equation of a tangent line, solve for y, and that's your linearization. And remember, this can be used to approximate the function f of x itself. Okay, let's try this on something. We'll use the function square root of 1 plus x. And let's find out the linear approximation of that function near x is equal to 8. Is there a question there? You okay? Good? Okay. Okay, so remember on the last page, all we're going to do is to find the equation of the tangent line at 8 and use the y equation, the equation of the line, to replace this. So let's have a quick sketch of this curve here. This is 8. If I'm putting 8 here, my y is 3, right? And that's the tangent line I want. So let's first find the slope of the tangent line, f prime of x. The function was 1 plus x to the 1/2. Slope is 1/2 times 1 plus x to the minus 1/2. At x is equal to 8. The slope is 1 over 6 when I plug in x is equal to 8. Okay, that's a 9. 9 to the power of minus 1/2 is 1 over 9 to the 1/2, which is 1 over 3. 1 over 3 times 1 over 2 gives me 1 over 6. Okay, now we write the equation of the tangent line at 8. Y minus f of 8 okay, so that's our f of 8 is equal to f prime of 8, 1 over 6 times x minus 8. And once again, that's just the equation of the tangent line, a slope and a point, just a very ordinary line. Let's solve for y. This is a 3, right? So 3 plus 1 over 6 times x minus 8. And then once again, that's the idea of linear approximations. Instead of doing this, using this function, radical 1 plus x, we can just use this equation of a line, a very simple equation of a line. If we don't venture very far from x is equal to 8, we will make some little bit of an error, because no matter how good approximation is, there's going to be a little bit of an error. But if we don't move too far from that, we should be okay. All right, so this is our linear approximation L. Any questions so far? Yeah. Equation of what? Right. Yeah, the purpose, this is a simple example here, but suppose this is a very complicated equation, got log, trig, exponential, and over some really even ugly looking thing. then if you want to work with that, it may be cumbersome. Maybe it's a better idea to work with a line, which is a simple shape. So this example here is just illustrating the idea there. But in practice, of course, this is normally far more complicated. Let's see how good approximation is. Okay, so let's use the technique here to find out what radical 9.1 is. The function we're basing all of this on is radical 1 plus x. So radical 9.1 can be looked at as radical of 1 plus 8.1, right? So that means my x here is 8.1. Remember, if we don't move very far from 8, our approximation should be pretty good. And we're not moving very far. 8.1 from 8 is a tiny little distance here. We expect a pretty good approximation. So we're going to use that L equation there. 3 plus 1 over 6 times 8.1 minus 8. (8.1 minus 8 is 0.1. That's 1 over 10. So that's 3 plus 1 over 60, which is 181 over 60. That's approximately 3.01667. Okay, the tangent line approximation says radical 9.1 is around 3.01667. Compare that to the true value of radical 9.1. 1. You put that into a calculator, you get 3.01662. Okay, so that's a reasonably good approximation. We're only off by 0.0005 out of 3 point something. Depending on what purpose you're doing this for, that could be an error that you can ignore, depending on, again, on what the application is. Right, does that make sense what I did here? Any question on this example? Now let's see what happens if we move far away from 8. From the picture here, notice near 8, the line and the curve are about the same. But if I move, say, all the way over here, obviously the difference will be very big. So let's move far away from 8 and let's go to radical 1. We know it should be 1, but let's see what the tangent line is telling us. Don't forget what the function is that we're basing the entire thing on. The function is 1 plus x under root. If you want to know radical 1, this means that your x is actually 0. Which is very far from 8 compared to 8.1, right? So we expect the approximation to be pretty bad. Let's see what the approximation tells us. So in the approximation, you put the x value in here, 0. And we get 3 plus 1 over 6 times 0 minus 8, which is 3 minus 4 over 3, and turns out to be 5 over 9. And the true value of radical 1 that you don't need a calculator for is 1. So you can see there's a pretty big difference here. Okay, and that's what happens, a very typical thing when you move far away from 8. And once again, how far is too far depends on what the function looks like. If the function is pretty erratic, then even a small distance can be too far sometimes. Questions? I don't know. 3 minus 4 over 3. What is this thing? That's 9 over... So that's what? 9 over 3 minus 4 over 3. Oh, 5 over 3? How about that? Is that better? Is that right? Okay, good. Now the point is, it is not 1, right? It's not even close to 1. Whereas in the earlier approximation, we didn't move very far, and the difference was small, very small. In most applications, that difference is negligible. Here, there's no application that will say the difference is negligible. Question on this example. Okay, let's do another one here. And this next one will actually explain one of the other things we saw a little bit earlier. Let's find a linear approximation of sine of x near x is equal to 0. So that's our sine. And the tangent line near 0 is this green line right here. And as you can see, near 0, that green line and the tangent line are not too far apart. But once we move to pi over 2, for example, the difference is going to be big. But if we stay near 0, we should be pretty good. Okay, so we first find the tangent line slope. So f prime of 0 is 1, right? Slope of tangent line. I use TL to stand for tangent line. And the point that we have on the tangent line is 0, 0. So the equation of the tangent line is y minus 0 equal to slope times x minus 0. Or simply y is equal to x. And so this is saying that that sine of x is going to be approximately equal to x if x is close to 0. Right? The tangent line equation is x. The function itself is sine. So here, this is something that's pretty useful. If I ask you what is sine of 0.2, now, without a calculator, you probably won't be able to tell me that. But if you know we can do this, then sine of 0.2 should be 0.2. Right? And this explains, this is another explanation to why the limit as x goes to 0 of sine of x over x is equal to 1. Okay? When we say limit x goes to 0, it means we're staying close to 0. And now we see that near 0, sine behaves just like x. So there's another explanation why this limit turns out to be 1 that we saw earlier. Earlier, we used a geometric and a table to see that this is 1. Here's another reason why it turns out to be 1. Okay, does that make sense? Any question? Okay. I want to revisit one of the pictures I sketched earlier. And sketch this kind of big because we'll be adding quite a few things to it. There's my function, and I want to do a linear approximation at x is equal to a. And there's my tangent line. Okay, so this is our linear approximation. If we go to a different value of x, let's say right here, we'll call this point right here a plus delta x. I'll make a change of delta x amount to a and move it a little bit to the right or to the left. It's the same idea, but I'll show to the right. This point right here, obviously, is then f of a plus delta x. The difference right here, this is delta y. And that's representing what the actual, the true change in the function value y when you make this change to x. So that's the true change. If you follow the tangent line to a plus delta x, then you get to this new point here. And you can see in general, it's not going to be at the same point, but hopefully it's near what it should be. So this difference right here this is the estimated change. And we'll call that change dy. We use d to represent the fact that we're kind of estimating what the delta change is. Delta y is the true change, and dy is the estimated change. In general, delta y and delta dy are not going to be the same. But if we make the change small enough, then they should be pretty close. Should be pretty close. Like in the last example with the 8.1, but if you move very far with the example of going back to 1, the difference would be pretty big. Okay, so let's find out what this dy thing is. To find dy, the easiest way to see what it is to start with the equation y is equal to f of x. If you take the derivative on both sides, you get dy dx is equal to f of x. This dy dx can, in this case, be looked at as some kind of fraction. So we're going to multiply both sides by dx. And what we end up getting is this funny looking thing, dy, f prime of x times dx. This is called a differential of y. All it is the derivative with dx multiplied to the right-hand side. In our problem here, this dx, in the context of linear approximation, dx is delta x, which is a small change in x. So this equation right here will give you the estimated change, the change you would get when you follow the tangent line. Delta y is the true change that you get when you follow the curve itself. Okay, so that's our differential. And you can see just by knowing the derivative and the change in x, we can find out the estimated change. To find the true change, we have to do this, which may or may not be easy to do depending on what f looks like. Okay, let's try this on something. Let's say our function is 4x minus x squared. And let's find out the true change in the function if we move x from 3 to 3.4. And we'll compare that to what the estimated change from linearization would tell us. And we'll see how good the comparison is. What shape is this? What shape is this function? Upside down parabola. Okay, tell me more about it. Where are the x-intercepts? Zero is 1. Yep. What's the other one? 4. Good. Excellent. So there we go. 4. And we have an upside down parabola. There we go. That's a nice parabola. Okay, so we're going to build a linear approximation at 3. So what is 3 is right here. And tangent line says near 3 will follow the green line. And 3.4 is somewhere over here. So that's where it should be. And this is where the estimated y of 3.4 would be. The difference between these two, this is our delta y, the true change in y. The difference between these two, that's our dy. D is estimating delta. That's the way to look at it. Okay? Okay, let's calculate the true change first. And that requires using a calculator. Delta y is equal to f at 3.4 minus f at 3. So you plug 3.4 into your function. 4 times 3.4 minus 3.4 squared minus 4 times 3 minus 3 squared. And this turns out to be negative 0.96. Not so bad. Oh, it's the value. Let's see what the estimated one would be. The differential dy is f prime, the derivative times dx. Derivative is simple. 4 minus 2x. And dx is dx. dx here is representing the change in x you made by making this change. We're going from 3 to 3.4. We made a change of delta x, which is the same as dx in our application here, which is equal to 0.4. Okay, so we move a little bit from 3. The important thing about this x right here we have to use 3 and not 3.4. And the reason is because that's where we built our linear approximation. So this is the starting / old value of x. And we use it because that's where the tangent line is built. We built the tangent line at 3. We're starting at 3. We build a tangent line there. We don't use 3.4. That's not where we build a tangent line. So what do we get? We get 4 minus 2 times 3 is 6 times 0.4. So that's negative 0.8. The true change is minus 0.696. The estimated change is minus 0.8. Again, depending on what you're doing this for, that may or may not be satisfactory. If you just want a big, rough ballpark estimate of the change, that's probably pretty good. The error is only about 10, 15, 20%. Maybe it's not so bad, depending on what this is for. Now the difference you can see, to do this, I would require a calculator to do 3.4 squared, or at least do quite a bit of cumbersome calculation to get it. Here, one derivative, plugging one simple value, I can do that. I can do this without a calculator. And if you imagine f of x being more complicated, then this would be very difficult to do, whereas this may not be very difficult. Okay, does that make sense? Any question? Okay, let's do one more example. Let's estimate e to the power of 0.1 using differential. Yeah. So what is it? What is it? Yeah. Yeah, what is it? What is it? That's what we want to find. That's the idea here. Okay, this is, you're right, it's a constant, but it's a number. I would like to know more about it. Okay. Now remember, everything is based on the tangent line, right? So here's our graph of e to the x. Let's say this is 0, and let's say 0.1 is right here. Now the closest place I can calculate e conveniently and accurately is at 0, right? The closest convenient, that's not how you spell convenient, the closest easy place to calculate e to the x is x is equal to 0, because I know e to the 0 is 1. That I know for sure, absolutely sure. You spell convenient. I can't. It's not a convenient word. Okay, so the idea is to use a linear approximation. We'll follow the tangent line to 0.1. I can use that to calculate dy. And once I know how much it changes, I'll add it back to 1. That should give me a good approximation of e to the 0.1. Right? Does that make sense? Okay. So let's do that. Y is equal to e to the 0.1. E to the x, sorry. That's the function we're using. Y is e to the x. The linearization at x is equal to 0. Let's get a differential here. Rather, let's use, the word should be differential, sorry. From linearization, but we want to use the differential. Oh, that looks horrible. Gee. Okay, now this will tell me estimated change. E to the 0. I would like to go to 0.1. So delta x is equal to 0.1 minus 0 equal to 0.1. So this is what we're saying here is by making a small change to x from 0 to 0.1, what kind of change are we making to y? Well, it's 0.1, right? That's a 1. That's 0.1. So we expect a change to e to the 0 of about 0.1 by moving from x equal to 0 to x is 0.1. Our dy happens to be the same as dx, coincidence. And this means that the estimated value of e to the 0.1 should be around 1, because that's my e to the 0, plus 0.1. This is my dy. I make a small change in x, and the resulting change in y turns out to be 0.1. And this should give me around 1.1. And someone with a calculator, tell me the true value of e to the 0.1. Who's got it? 1.105, 17? 17. Okay. Right, so it's not bad, right? It's not bad. It's pretty close. 1.1, 1.10, 1.1 versus 1.11. The difference is very small. So that's another, this is the kind of thing that you can use to estimate the value of a function close to a point where you know easily and accurately, and then make a small change from that. All right, that's it for today. Have a good weekend. See you Monday.